Hey, statisticians! I'm at your favorite place this time. You can tell. See? I'm lonely here without you. Okay, so if you did not get all the notes on Friday, they are above. We talked about these questions after we watched a video, a really awesome video on manatees, I might add. So, I don't know, you're going to have to come in and watch that video. So, we talked about, of course, all the way, or why we're now using scatter plots, because we have two sets of data, not just one, on individuals that we are measuring. And we talked about what goes on the X and Y axis, and we talked about how we're going to remember how to describe scatter plots using SOFA. And so the one thing that you need to remember when you're describing is that you must graph it. So we're going to plot now on a scatter plot, and we're going to do that first, and then we'll add all of the SOFA stuff to talk about the graph. Now, keep in mind that the explanatory, of course, goes on the horizontal axis, and the response variable goes on the vertical axis. But what if I had something like math SAT and verbal SAT, and I asked you to tell me which one explains the other? I'm pretty sure you'd do one of these. I don't know, Torres! And you'd be right. So if there's no real distinction, then either can go on the horizontal axis. I don't have to worry about trying to decide for sure which one goes or which one is the explanatory. So in this particular case, you could have math and then verbal, or you could have verbal and then math, because there's no real distinction as to which one is the explanatory. So something that's kind of cool about scatter plots is I could add a categorical variable by doing something with either plus signs or little squares like your calculator does. We'll take a look at some of these in class tomorrow. Or I could use colored dots. So I just have to remember that I have to put a key. So let's say that green is boys and pink for girls. And so then you can see both sets of data on my same scatter plot. Pretty cool, huh? Like I said, your graphing calculator will do this. I show you tomorrow. So now we're going to start talking about a term known as correlation, and the symbol will be R. You'll see that all year. And it measures both direction and strength of your data to a linear model. Very important that you remember it measures the direction and strength for a linear model, or a linear relationship between two quantitative variables. And the formula is kind of scary looking, right? But the reality is you've actually seen this very stuff before. So if you look at this, I want you to think, where have you seen this before? Where you have an X and you're subtracting a mean and you're dividing by a standard deviation. Hopefully you said z-score. So this is a z-score for the X quantity, and then at the same time over here this is the z-score for the Y quantity. So I could just say, oh, it's a summation of all the z-scores for each individual's data set. So remember, I have a data value, an X and a Y for each person, and it's the z-score of that X times the z-score of that Y. Notice they're being multiplied. And I'm doing that for every individual, and then I'm going to add up, summation, all their z-scores, and divide by n minus 1 like I was doing in standard deviation. Do you need to memorize this formula? No. I want you to find it on your formula sheet so you can tell me exactly where it is tomorrow. But if the association is greater than 0, then I have positive, obviously, because it's greater than 0. I'm sorry, I meant if R was greater than 0. And if R is less than 0, then it's negative. Sort of makes sense, doesn't it? And if R equals 0, then there's no association. And if all the data values lie on a line, then R is either positive or negative 1. And you could see that in both of these. This would be a positive 1. And this one, if they all lie on the line, pretend I hit it, equals a negative 1.